All right. Next topic. Yeah, we're coming up on an hour here, but I think we're going to be able to finish just a bit over it. A word. Word size. What is a word? Well, first off, very generically, a word is a fixed number of bits or bytes. Okay. So a word might be 8 bits, or it might be 16 bits, or it might be 32 bits. It's almost always a multiple of 8. Okay. What is it from the point of view of the CPA? Well, it's a unit of data transformation. So if the ALU is going to add together two numbers and generate a third one, each of those input numbers and the output number is typically going to be a word. And so all three of those, of course, are going to be the same size. So we can think of a word as being the size of a data item that the CPU manipulates when it executes a quote-unquote normal instruction. Okay. Another way to think of a word, and it doesn't always work in a modern processor, is as the size of a memory address. Okay, and in the current generation of Intel CPUs, for example, the size of a memory address is 64 bits. So you might assume, for example, that a word in a modern Intel CPU is exactly 64 bits long. Okay, you, of course, would be wrong. Because, once again, if we come back to this, let's see, let's go find it in the basic execution environment. Okay, I found it. It's at the very beginning of chapter 4 in the software manual of the data types. Okay, so the manual talks about something called fundamental data types, but this doesn't mean what we were talking about in chapter 3. When we were talking about data types in chapter 3, we were talking about integers and memory addresses and IEEE 754s and whatever. What they're really talking about here is words. And let's look at this very first sentence. The fundamental data types are bytes, words, double words, quad words, and double quad words. Okay, summarized in this figure. So byte, as we already know, is 8 bits. For Intel processors, a word is defined as 16 bits. 32 bits is a double word, 64 bits is a quad word, and 128 is a double quad word. Okay, so you might say, okay, well, the word size is 16 bits, but what about these doubles and quads and double quads? Okay, well, one of the complexities you run into with Intel processors is, remember Intel made the original processor that was in the original IBM PC. Okay, that was an 8088, shortly followed by the 8086. Okay, the word size on that 88 was 16 bits. Okay, that's a word. Okay, now you may not realize this, but every Intel processor, except for a few oddballs, okay, all the commonly used Intel processors in laptops and desktop computers and what have you, made since that originally IBM PC, all maintain backward compatibility with that. If you had a set of instructions that ran on that original 88 processor back in 1981, you can run that exact same set of instructions on an Intel Core i7 second generation. Okay, so that's over 30 years of backward compatibility. Okay, the reason they keep saying a word is 16 bits is because a word was 16 bits in 1981. Okay. But the reality is, if you look at one of these Intel modern processors, the true word size, the one they use the most often, is 64 bits. But we don't call that a word in Intel speak, we call that a quad word. Okay. So as that figure quite aptly illustrated, we've got word sizes running from 16 to 128 bits, from word to double word to quad word to double quad word. So this whole issue of word size has gotten a little more complicated. Okay, it's probably a little easier to think of it in terms of memory addresses. Okay, a modern Intel CPU since about 2004, 2005 has used 64-bit memory addresses. Okay, so for practical purposes, to make sure we're all speaking in the same terms, the modern Intel CPUs are 64-bit word size processors, as are most of the CPUs from anybody else, for example, IBM Power CPUs. That said, both the Powers and the Intels can occasionally deal with double size words to operate on quote unquote big pieces of data. And when would you do this? Well, for example, you might do this when you're running a database management system doing text searching. You might operate on these bigger pieces of data when you're, say, encoding an MP3 file, okay, or encoding a video file. Okay. But for most of the quote-unquote normal stuff, add, subtract, multiply, divide, run my word processor, run my spreadsheet, play my video game, we're generally dealing in 64-bit chunks. So it's pretty safe to say that modern processors are typically 64-bit word size, okay, with the occasional diversion to double that for specialized processing. Okay. Why do we care about word size? Well, word size has a direct impact on performance. Okay. What is that impact? Well, it boils down to this. What is the size of the pieces of data I normally need to manipulate? Okay. And is my CPU word size at least that big? Okay. The circuitry of the ALU is designed to manipulate all of the bits of a word in parallel when it executes a single instruction. Okay. So if I'm adding a 32-bit number to a 32-bit number, think of 32 individual add operations, one for per bit position going on. Okay. Now, of course, it gets more complicated than that because, if I've got a 1 here and a 1 here, that generates a 0 with a 1 carryover into the next bit position, and I've got to account for that carryover effect. But, just think conceptually of, just the way you would lay it out on a board if you wrote the 32-bit number on the top and you wrote the 32-bit number on the bottom and you lined them up on the decimal or radix point and you kind of added down the columns. Think of the CPU internal circuitry as being organized, in more or less that fashion. Okay. So, larger word size implies that the ALU is bigger and more complicated, okay, because there's more of these parallel processing circuits. That increases CPU size and complexity. It increases its expense, and all other things being equal, it lowers clock rate. Okay. And actually, this is a very good diversion because if you look towards the end of the chapter, there's a discussion of transistor count and clock rates and other things and how Intel processors have changed over time. And what you might notice is clock rate took a pretty steady march upward from the earliest Intel processors right until the early to mid 2000s, and then it kind of hit a wall, kind of hit a snag. And it didn't go up much. As a matter of fact, it actually stayed the same or went down a bit and then started a very slow march up from that lower position. What accounts for that dip in the curve? That dip in the curve is the switch from 32-bit to 64-bit word size. Okay. When 64-bit word size came into vogue in the mid-2000s, and it had to come in vogue for reasons we'll discuss later, all of a sudden clock rate became a problem. Okay. It also became a problem for some other reasons that have to do with processor fabrication. Okay, but the bottom line is, if you increase word size, all of the things being equal, you slow clock rate. Okay. Now, let's talk about mismatches between the CPU word size and what it is we want to add, subtract, multiply, divide, or compare. If the CPU's word size is bigger than the size of the data items in the program that I need to manipulate, then there is no performance penalty. Okay, so if I've got a 64-bit CPU but I'm only adding together 32-bit numbers, well, that just means I got a lot of extra zeros that I'm carrying through. So in theory, I'm wasting a bunch of circuitry, and to the extent that extra circuitry is slowing things down, that's bad. But from the point of view of, does it take any more time to add a 32-bit number versus a 64-bit number on that CPU? The answer is no. Okay, so there is performance being suboptimal, but the suboptimality comes from the fact that we've got more CPU than we need. Okay, think of it this way. It's kind of like going out and buying a sports car for your grandmother who's only going to drive it to the grocery store once a week and to the church on Sundays, and she's never going to get above 25 miles an hour. It really doesn't make much sense to, buy her the turbocharged V6 with the fat tires on the back and the spoiler, unless, your grandma just likes to look cool, I guess. But you're paying for a lot of engine and a lot of performance that you're not using. Okay, so that's the suboptimality. It's not that, you know, grandma takes more time to get to church. It's just that, you know, she's, you know, using a car that could go 150 miles an hour to go 25 miles an hour. So it's a waste. Okay. Second possibility, CPU word size is exactly the same as the size that you're going of the data you're going to manipulate. Okay. In that case, that's an optimal scenario. That's a best case scenario. Okay, so your performance of the hardware exactly matches the data you need. You're spending money, you're spending the right amount of money to do what you want to do. Okay, now let's talk about the next one. CPU word size less than program data size. Okay, well, you say, well, how could that be? Well, it could definitely be. For example, just earlier in this video, we talked about the original IBM PC, which had an Intel 8088 in it, which was a 16-bit processor. Actually, it was a 16-bit processor with an 8-bit I/O bus. Okay. Well, the largest number, you know, unsigned integer you can represent in 16 bits is 65,535, I think, something like that. And yet, on this original IBM PC, you know, there was this primitive program called Lotus 123. Think of that as the forerunner of Excel. And there were people, you know, using that spreadsheet program to, you know, manipulate some fairly large numbers. You know, let's say, for example, there was somebody in the U.S. Office of Management and Budget who was using it to estimate next year's deficit, which in 1981 was a lot smaller than our current deficit, but the bottom line, it was substantially larger than 65,535, unless you left off a lot of zeros. So how do you write a piece of software to manipulate numbers in the billions when you're on a 16-bit processor, which, in theory at least, can only represent number in the thousands? Okay. Well, the answer is you break the data item into word size pieces and you do operations on the pieces, okay, and then you reassemble the pieces back to make the whole. Okay. Now, think about that for a minute. Does it sound like it might be a little complicated? Yes. Okay. So breaking the big numbers up into little numbers, finding algorithms by which you can operate on the pieces in such a way that you can then put the pieces back together to produce the result and have it correct, that tends to be a fairly complicated algorithm. Okay, complicated algorithm means performance penalty. The bigger the mismatch between the word size and the data size, the bigger the performance penalty. Okay. So the CPU shouldn't be lower, it should be slower. I'm sorry, cost of the CPU is lower because it's simpler, but the performance penalty to run the programs is huge, 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 huge. Okay? So, why do we care about CPU word size? Well, we care about CPU word size because in general we want to be here. We want a CPU that has a word size as big as the data we normally manipulate, okay, so that we are basically balancing performance and cost. We don't want to be here because we're paying for more than we need, and we don't want to be here because we're buying less than we need and paying a huge performance penalty in the process. Okay. So, what is the typical size of data we need to manipulate? Well, the answer is it depends. Okay. If we're talking, say, your Excel spreadsheet, 32 to 64 bits is probably enough. Okay, the largest 32-bit number is 4 billion. The largest 64-bit number, you don't even want to write that number as zeros on the board. So somewhere in 32 to 64 is the sweet spot for most numeric processing, unless we're talking about some very specialized applications like, say, weather forecasting or like trying to control the trajectory of a satellite, or I'm sorry, a spacecraft heading from here to the nearest star. Okay, so, but for quote-unquote the ordinary stuff, 32 to 64. But there are some things bigger that we will occasionally want to manipulate. So, for example, when we're dealing with video files, okay, how big's a video file? Well, God, this one's probably going to be 100 megabytes by the time we're done. That's a big video file. And you can bust it up into fairly small chunks because, think of each pixel on the screen as being represented by a few bytes of information representing intensity and color. But if we can process that in larger size chunks, either for display or encoding or whatever, then the computer is going to be more efficient. Okay, so for some things like video processing and for many database or text mining applications, bigger is definitely better. But those tend to be specialized applications. For a lot of the ordinary stuff, 64, 32, maybe 128, somewhere in there is a pretty good match. Okay? So that's where we want to be in terms of word size, and fortunately we live at a time where that's pretty much right where we are in terms of the capabilities of a modern computer. Roll the clock back 20 years ago and we were here. And that's one reason why what a computer could do back then was limited compared to what it can do today, because there was an awful lot of performance penalty going on because of this working piecewise on larger pieces of data. Okay. So, summarizing, as we said, for business applications, 32 to 64 bits is pretty typical. For scientific applications, and you could throw 64 to 128. And for database and multimedia applications, it's variable, but generally more is better. Okay. We go back to the early days, 8 or 16 bits was typical word size. That's basically all we could do. Big performance penalties. Okay. That gap between what we had and what we needed was there until roughly the mid-2000s. Okay, right now we're in the era of 64-bit word size, and as I said earlier, with the occasional diversion into doubles of that. Will we ever get true 128-bit CPUs? Hard to say. Bottom line is, most applications don't need them. Okay, if you can deliver it for zero cost and zero performance penalty on clock rate, then sure, go ahead and take it. But assuming there will be some cost for those extra 64 bits, be it either additional cost of the processor or slowing down of the clock rate, then for quote-unquote most business applications and a lot of desktop applications, that 128-bit really wouldn't be an advantage. It would definitely be an advantage for database servers. It would definitely be an advantage for your PC if your PC was going to do nothing but multimedia all day. And of course, take Facebook and YouTube to their, stretch that trend out another 10 or 20 years, and maybe that's all computers will do in the future. In which case, maybe we will not only have 128-bit CPUs, but we'll have 256 or 512 or 1024. Hard to say looking forward. All right, so we're over an hour. I'm sorry, but we are fortunately on the last slide or two. Okay, and this kind of brings us to the summary, so I don't want to break here and go to part 3. Let's just finish this up. Okay. We have two quote-unquote competing philosophies of processor design. And the reality is they're really not competing that much anymore, but we'll talk about it anyway, at least start out that way. We have what's called reduced instruction set computing. And this is a game IBM likes to play, and they like to tout it up in all their power documentation. And there's several ideas behind reduced instruction set computing. Okay. First one is avoid complex instructions that we don't need. Okay. Do we really need 1,000 instructions in the instruction set? Okay. Or can we get by with a dozen or 50 or 100? Okay. Why would we want to consider fewer? Well, remember that control unit that's doing the fetch. Larger numbers of instructions tend to apply variable-sized instructions. They apply large tables. They apply complex decoding circuitry. Okay, that decoding process and fetching process happens every clock tick. So if that's slow, even if it's only slowed up a little bit, that's a performance penalty that's applied billions of times per second. So part of the RISC philosophy is keep the instruction set as simple as possible. What that does in theory is speed up fetches and decoding, which speeds up everything. Okay. So by avoiding those, we minimize the number and complexity of instruction formats. We want to minimize the maximum instruction length. Okay, and one way to do that is to avoid complex instructions that combine data movement with transformation. In other words, instructions that have memory addresses as operands. Okay, instruction sets that have no instructions that do this are sometimes called load store architecture. Why? Let's back up here a second to our discussion of move. And you'll recall that we have a move from a memory address to a register is a load, and a move from a register to a memory address is a store. Okay. So come back here to load store operation. So load store architecture implies that the ALU only reads from general purpose registers. If you want something in a GPU, you have to issue an explicit load or move instruction to get it there. If you want something to go from a general purpose register back to memory, you have to issue an explicit store or move instruction to get it there. Summarizing all this mess, less is more. Okay, and the best example of this in the modern world is IBM Power CPUs. Okay, so let's compare that to CISC, complex instructions. Okay. First off, you can think of it as the opposite of RISC, and if you want an example, well, there's your example. Okay, there's your example with, hundreds of data types, 5 different word sizes, tons of registers, etc., etc., etc. Okay, so what have I just done? Well, I haven't really described IBM versus Intel. What I've really done is I've painted 2 ends of a continuum. Okay, if I take RISC to its logical conclusion, okay, if I really eliminate all unnecessary instructions, if I really minimize the number and complexity of formats, minimize instruction length, only go to load store, guess where I wind up? I wind up back with that dozen to dozen and a half instructions that we started this discussion with. Okay. So RISC in theory is the processor we had 50 years ago, just manufactured with modern methods, made 64 or 128 bits wide instead of 8, and, operating at gigahertz clock rates. Okay. But in theory, if you really take RISC to its extreme, you've simply got a very fast processor from the 50s. Okay. Complex instruction set computing, well, certainly the IBM folks would argue that Intel is all the way out at that end of the continuum. But as you dig under the hood, what you find out is, Intel's got a lot of RISC features buried inside of it. Okay. So rather than paint these as real competing products in the modern world, simply think of these as ends of a processing continuum with particular CPUs falling somewhere along that continuum. So if the R is all the way at the RISC end and the C here is all the way at the CISC end, maybe IBM's sitting about here and maybe Intel's sitting about here. Nobody's really all the way at one end or the other. They're all a compromise in between. Okay? RISC, IBM clock rates tend to be a little higher, okay, for the same process size because their control units are simpler. They've got simpler fetches, faster fetches, and therefore higher clock rates. However, because they're missing some of those complex instructions that are sometimes needed, sometimes the program slows down because it's got to do more, issue more instructions to do something that on an Intel processor you could do with a single processor. Okay, so the basic trade-off is here. Okay, in theory, you're going to get a faster clock weight with a RISC versus a CISC, all other things being equal. Okay, and in theory, the number of complex operations in a typical program is small, and therefore RISC is going to be better because you're going to not have a lot of extra overhead associated with complex instructions you don't need. That might be true in some very specific scientific programming environments, and frankly, that's one of the reasons why IBM tends to dominate in supercomputing. Okay, it's not that it's in some sense IBM, because it follows the RISC philosophy, they're somewhat more optimized to the fast computation. Whereas Intel's CISC designs that have a lot of complex instructions are more attuned to the kinds of applications where you would need those complex instructions. Think business apps, think database processing, think data mining, things like that. Okay, but the contrast between the two is not really as stark as either IBM or Intel would lead you to believe. And really, it's IBM who's kind of ringing this bell all the time, because both camps borrow heavily from the other's best ideas. Okay, and that's about as much as I want to talk about this. I'm sorry this was a very long video, an hour and 20 minutes almost, but this was a very complicated set of topics to work through. That concludes this particular video, and hope it sheds some more light on these topics beyond a simple reading of the textbook chapters.